So in today's lesson, we're going to be talking about a little bit more about the plant kingdom. And as in most new big topics, there are usually some pretty specific terminology that we need to discuss before moving on. So that's what this is going to look like today. So I've given you the option to simply read through the note, but if you also would prefer to have sort of an explanation to accompany the note, here it is. So we're going to be talking about the plant life cycle. And so when we talk about life cycle, we're talking about, seed to plant, back to seed to plant. That's a cycle that continues. So, but, with humans, I think we sort of can envision how that happens. Plants are a little bit wonky, and it's not an uncomplicated process. So like I said, there's some terms we're going to need to know before we move on. And luckily, we're going to see these terms again when we take a look at our genetics unit coming up. So, so the first term that I want us to know is diploid. And so we've been doing a lot of exercises in biology so far, talking about prefixes and suffixes and how those can inform us about what it is that we're talking about, give us some insight. So the prefix di is one that comes up a lot. I'm hoping that you recognize that as meaning two. And so we can translate the term diploid into meaning having a full complement of chromosomes, which means two sets, right? So remember that in every regular body cell, we're going to have two sets of chromosomes, one from each of our parents, right? So for humans, we would say that the diploid number of chromosomes is 46. So half of which are coming from your mother and half of which are coming from your father, right? So the diploid number refers to the number of chromosomes in most of the cells in your body. Conversely, we should also discuss the term haploid. So if we're talking about an organism's haploid number of chromosomes, we're talking about them a single set of chromosomes. So it's kind of misleading because it's not really half versus double, it's half versus full. So having half the number of chromosomes means having a single set. So only very specific cells in our body, in a human body, will have a haploid number of chromosomes, and those are our reproductive cells. So for example, for humans, if our diploid number is 46, what must our haploid number be? Well, I'm hoping you deduced that that would have to be 23. There we are, that's a little bit better. Okay, so diploid and haploid, really important terms for us to know, not only when we talk about plants and alternation of generations in the plant life cycle, but also coming up in our genetics unit. Another of two very important terms that I'm putting beside each other, I'm juxtaposing them because they are related. Mitosis and meiosis. So mitosis you should be familiar with from grade 10, just remembering, prophase, metaphase, telophase, anaphase, telophase, and so on and so forth. And so when you think of the word mitosis, I'm hoping you're thinking about just the reproduction of regular body cells, right? So just cell division. And now that we understand what the word diploid means, we can add in that term diploid. So mitosis deals with cell division when we're talking about cells that have just the full complement of chromosomes, right? So for example, most of our body cells are going to undergo reproduction, are going to undergo cellular division by the process of mitosis, right? So a skin cell, for example, a blood cell, and so on and so forth. So, mitosis is a process of cell division that results in us producing new regular body cells, which have a special name, and that name is a somatic cell. Okay, so when I say a somatic cell, I mean just your everyday body cell, every cell except for your reproductive cell. So then the question becomes, well, what is the process that causes our reproductive cells to divide? Well, I'm sure you've guessed it, that is meiosis. So meiosis is a type of cell division that will produce haploid cells. And so in humans, that is the process by which we are able to produce sperm cells and egg cells. Okay, so meiosis, unlike mitosis, results in cells having the haploid number of chromosomes, right? So in other words, one set. Okay, so those typically will become the organism's reproductive cells. We're going to talk a little bit more about that. So now that we've gone through some of the basic terminology that is important to gain an understanding of the plant life cycle, I think we're ready to kind of just go over some basic differences between what we observe with animal cells versus what we observe with plant cells. So there are some definite similarities for sure. So a lot of this will seem familiar to you, but there are also some like oddities that I think need to be talked about. So first of all, let's start out with some of the basics. In both plants and animals, a diploid cell can become another diploid cell through the process of mitosis. So a diploid cell can undergo cellular division by the process of mitosis to produce other diploid cells. So a good example of this would be like, let's say you have a skin cell, right? That skin cell can become another skin cell, and both of these will have the same number of chromosomes. You're starting out with a full complement because it's diploid, ending up with other skin cells that also have a full complement, and that happens by the process of mitosis. That happens in animals, so likewise in plants, you might have a cell in a root of a plant, and that root wants to grow, so it's going to divide and produce new root cells, but both the original root cell and the new root cell are both going to be diploid in number, and the process by which that happens is mitosis. So there's that. So plant and animal cells are the same in that respect, in that mitosis will take a diploid cell in both plants and animals and produce another diploid cell. Another aspect that both animal cells and plant cells have in common is that in both of these, diploid cells can become haploid cells by the process of meiosis, right? So we take a cell that has the full complement, right? Let's say 46, and through the process of meiosis becomes a haploid cell with 23 chromosomes, right? And that's just talking about humans. So, let's look at this. Well, we might have, and later on in the course, we are going to talk about the specifics here, and I didn't want to overcomplicate it with new terminology, but we're looking at, let's say, a cell in the testicle of a male who's reached puberty. Then, those cells will eventually divide to become mature sperm cells capable of fertilizing an egg. So how does that happen? Well, that specialized testicular cell will have 46 chromosomes, but then will divide to become a sperm cell through the process of meiosis, and then that will result in a sperm cell having 23 chromosomes. Okay, in the same way, there might be some specialized flower cell with a full complement of chromosomes that through meiosis will become a pollen cell, and a pollen cell is a reproductive cell in the flower, so it will be haploid in number. You may be wondering, well, what is the point exactly of having a haploid cell? Why is that important? Well, I want you to think about the process of fertilization. So I'm going to use humans as an example because I think it makes the most sense, right? Remember, if a testicular cell has 46 chromosomes, let me see if I can do this here, 46 chromosomes. And a sperm cell has 23. Then we would say, well, the same would be true for a human egg as well, right? The female egg. So, what would happen if the sperm and the egg were not haploid but diploid in number? Well, that wouldn't work. We know a sperm with 23 chromosomes from dad is going to join via fertilization with an egg cell with itself being haploid in number, 23 chromosomes, to form a zygote, and that zygote, eventually becomes the baby, right? It multiplies, but it makes sense because now that zygote has the full complement of chromosomes. So every cell in that newly formed zygote, which becomes the embryo, becomes a fetus, becomes the baby, is going to have the full complement, one set coming from dad and the other set coming from mom. Really weird and unique to plants. This does not happen with humans or animals for that matter. In plants only, they can take a haploid cell by the process of mitosis and make another haploid cell. That is unique to plants. Animals don't do that. So that brings us to a process that plants undergo for reproduction. That plant life cycle has a special name. It's called an alternation of generation because it includes, part of its existence is in the haploid stage and part of it is in the diploid stage. Okay, so and each of those is called a specific generation. So you have your haploid generation and you have your diploid generation, which is kind of wonky. Okay, so I'm going to show you a diagram that kind of gives you a good overview of this. Let's take a look. All right, so take a look at this diagram. Maybe pause the video, take a look at it, and try to put some of these pieces together before we start a discussion. I think it's always helpful for us to kind of spend a couple minutes exploring, trying to pull out any important aspects of a diagram before discussing it. I think it'll be more meaningful. So now hopefully once you've done that, you've taken a look at this and tried to figure out what some of the symbols, terms might mean. Let's start with the n and the 2n. So I'm hoping you were able to think of n as being a variable, and n often represents number, which in this case it does, and specifically it refers to the number of chromosomes. So when we talk about 2n versus n, well, 2n simply refers to, that really is just a way of representing the diploid number. So I'm going to try to write out diploid here. So I don't have my stylus, and I'm just using the little pad on my lovely computer. So there's diploid. Oh, this is painful. So there's that. So 2n refers to diploid. And the n, of course, then I'm just going to write out the h, meaning haploid, just to save us all from this painful experience. So there's the haploid number. So in other words, the plant has two distinct plant forms, one of which is a plant that has the haploid number of chromosomes, and the other plant form that has the diploid number of chromosomes, right? And so we consider the haploid existence to be the gametophyte generation, and the plant form that has the diploid number of chromosomes, we call that the sporophyte generation, right? So the sporophyte eventually divides via meiosis to become haploid spores, become spores with a haploid number of chromosomes. Those spores, which are haploid in number, will divide via mitosis to produce gametophytes. Okay? Those gametophytes are, of course, haploid in number, and they eventually become gametes. And remember, gametes are just sex cells. We want those sex cells to be haploid in number because if we have a male sex cell and a female sex cell, they're going to fuse to become, each of them are haploid, they're going to fuse to become a diploid zygote, right? And that diploid zygote is going to divide and become the mature plant. So that's a good overview of the process. I like this diagram for that reason. It's pretty simplified. But I do want you to watch a YouTube video that I posted in our Google Classroom that talks about ferns specifically in their alternation of generation. That does he's a little bit quirky, but I think he does an excellent job of presenting the ideas related to alternation of generation. Okay, few more details here that I want to talk about before signing off for the day. Okay, so I apologize for the small writing here, but I want to be able to reference the diagram as I talk you through these little points here. So in the gametophyte generation, we're talking about haploid cells producing haploid gametes. And then we see in the sporophyte generation, diploid sporophytes producing spores. And both plants need both of these generations. It's important for them to be able to go through their life cycle. We say that this is considered sexual reproduction because gametes are formed, right? Gametes is a special word for sex cells. And as I kind of give you a sneak preview, you're going to be looking at a video that will show you in ferns specifically how, the sporophyte appearance of the plant is super different from the gametophyte form of the plant. But they will both be considered the same plant species, just existing in very different forms, which is super odd, but also kind of cool. So look for the link to the video on ferns that will help to, I think, clarify a lot of these ideas, create some visuals and some applications of these ideas. I think it'll be helpful for your understanding. In addition, you should be looking for a worksheet asking you to explore the differences between non-vascular plants and vascular seedless plants, specifically ferns, etc. And I hope that will consolidate your understanding of those ideas. Also, we will be discussing all of this in class when we come back together tomorrow.